Hello everyone, my name is Clemente, and today I'll be presenting to you the modeling of a wave energy converter based on the real oscillations of offshore floating platforms with DualSPHysics, within the scope of the 5th DualSPHysics user workshop. So let's get to it, shall we? I'll start off with a brief introduction, then I'll discuss the key features of the Emotions, which is the wave energy converter that I'm developing in my PhD program. I'll then address the numerical modeling stage, which includes ANSYS Aqua and DualSPHysics. Then I'll discuss model calibration procedures with experimental data, present and discuss some preliminary results, and conclude with some remarks and future work prospects. Starting off with the introduction, as you probably know, there are hundreds of concepts around the world, but there's still not a winning horse, in the sense that there's still not something around which the sector can rally around. However, many WECs, a new generation of WECs, is being developed and is being demonstrated and optimized to reach that goal, that dream of commercial deployment. Hopefully we can get that someday. And how can we get that? Through composite modeling approach that combines the best of two worlds, physical modeling with numerical modeling. On the latter, you have two big families, let's say, which is computational fluid dynamics, or CFD, and boundary element method codes, or BEM. Three questions arise here: which one to use, how to use it, when to use it. You have to answer these questions for any WEC, including the Emotions. And the Emotions is what we're going to talk about next. It's a novel WEC, and depending on your reference system, you can it works by converting wave or wind-induced roll or pitch oscillations of multi-purpose offshore floating platforms into mechanical energy. And then you should have a PTO, a partake of a sliding in principle, that converts that mechanical energy into electricity. As you can imagine, it's a very simple concept, only has three components, which is a floating platform, can be generic, can be optimized, a superstructure, which can be at tech level or within the hull, and the power takeoff, which in principle should be an electric generator. It's adaptable, as I said, for any floating platform in principle, and capable of protecting the sensitive equipment within the hull. So you can mitigate the costs inherent to maintenance and replacement. If you want more information, you can check out the proof of concept study. I have the link here in this slide. But there's a big challenge here. How do you describe this? How do you mathematically decompose these physical interactions? Because you have wave structure interactions, which you can consider to be linear, but you shouldn't. They should be non-linear, because that's a reality. And to that, you add non-linear structure-to-structure interaction between a sliding PTO and a platform. So you have a very tricky, very complex problem, which entices PTO forces, power estimates, and end stops. And one way to solve this problem is through numerical modeling. And here, as I said, you have two big families. One, which is the boundary element method-based family from ANSYS Aqua. ANSYS Aqua is a software. It deploys BEM codes, and in particular potential theory. It's very fast, very accurate, has been used in the industry for many years, but it has a big no-no, which is it neglects the nonlinear terms. You can introduce them, but it's just a semblance. It's not the real thing, let's say. So it's more suitable for small wave and body motion amplitudes for operational conditions, let's say. Hence the necessity of something like DualSPHysics, which is based on SPH formulations and the Lagrangian meshless method. It's more accurate, more realistic, because it includes the nonlinear terms. You can also include the structure-to-structure interactions, moorings, although you can also include that in Aqua, but it's still important to have all of these features. However, the simulations are long, are complex, and it requires further validation. Even so, it is very promising. And why? This is why. The model on the left is in ANSYS Aqua. I can build this in one day, easy. The second one is from the Emotions, and the video you saw on the right is also from the Emotions in DualSPHysics. And this was done in like 2 weeks. And in these 2 weeks, you have to bear in mind, I knew virtually nothing. So I went from zero to this in about 2 weeks with the excellent assistance of the team at Torrency, to whom I thank gratefully. And this is a very important thing. In DualSPHysics, we have fast calibrations and simulation of the emotions variance, but you're limited to the considerations of potential flow theory. And there's also limitations to the experimental that you have. However, with DualSPHysics, you can, although you are also limited by the experimental data, you can have a more realistic portray of the problem. And we started off at 2D, but we found out that it was better to go to 3D to account for all the hydrodynamic response and all the wave structure interaction problem. However, the domain is very large, so add to that the limited data I had from the experiments, and I had a bit of a problem. And to solve that problem, I carried out a new experimental campaign, and also I upgraded the CPUs that I use for the simulations with DualSPHysics, and also I was able to have access to the GPU cluster at Torrency. Again, I thank the team there, to carry out the simulations with DualSPHysics. Now let's get to the comparisons. This is the experimental setup, let's say. It was carried out at a geometrical scale of 120, and I considered 3 physical models: half cylinder, half sphere, and the trapezoidal prism. You can see the pictures in this slide. Several tests were carried out, namely 3 decay tests, tests with regular waves, irregular long crested waves, and extreme sea state. So a very thorough analysis of the hydrodynamic response and the hydrostatic properties. And this allowed me to get a good calibration of the DualSPHysics model. However, I am bounded by the limitations of potential flow theory. And for example, for the case of the half cylinder, I actually got rotations of up to 30 or 40 degrees. So in that case, potential flow theory, BEM codes, they fly out the window in terms of accuracy. Hence the necessity of DualSPHysics. We started off with the half cylinder 3D model at the full scale, following on the fluid similarity criteria. And the first results, unfortunately, were not encouraging, because the results were bad. I'm going to be honest with you, they were bad, period. The motions in terms of amplitude were very low, the natural period was incorrect, a lot of inaccuracies. So we took measures. What did we do? We checked the moorings to make sure that everything was correct. We adapted back to the original 120 scale. We introduced gain stroke. We introduced also the dynamic boundary conditions with the new DualSPHysics version. And this was done, as you can see, successfully. You can see the model setup in this slide. And here you can see the XML, the various components, the piston, the tank itself, the fluid, everything, including the moorings. We also introduced some layers, some damping zones to reduce the domain even further. And the results improved massively. It's like night and day. We got good results for the free surface elevation, good agreement between theory and experiments, correct natural roll period, correct draft, higher roll amplitudes. However, there's still some differences. As you can see, for example, on the bottom from the 3 decay test, there's still some differences. There's a sort of excessive damping effect, and this also causes the amplitudes to be somewhat slower than expected. And there are many reasons for this. You can argue that it's due to low resolution, you can say it's mooring stiffness that's incorrect, you can say that DualSPHysics is introducing excessive damping into the problem, and you can argue that this can be solved through the introduction of dynamic boundary conditions combined with an even higher resolution, something more thorough, more meticulous, to try to solve the problem, but this is going to be computationally expensive. It's like I said, we had good results actually, especially for a even pitch. There's good agreement, but for sure there's some differences, as you'll see in the next slide. So a big discussion is, how does this evolve with a longer simulation? Does this stabilize? Because right now we only did for 30 seconds, and For example, you can see here that we even changed the mooring stiffness rather recently, and no big differences there. So this is not the justification. There are some differences, but we're still not sure on what might be. We have some hints, but it's something to discuss and something to improve. However, we believe that we are in the correct path towards having good results. To conclude, it was feasible to set up the DualSPHysics model for the half-C invariant. Although we had early inaccurate results, they improved massively afterwards after the adaptations. However, we're still getting a sort of overdamped body motions, and this can be attributed to resolution, viscosity, mooring, or other factors. Hopefully, in the future, we'll be able to carry out longer simulations with upgraded GPUs to get better and longer results. And in terms of prospects, I'm very interested in continuing to use DualSPHysics because it's very accurate, very stable, can be used complementary to ANSYS Aqua. I can compare the experimental results with the numerical results, hopefully for longer simulations above 50 seconds and for other wave conditions, particularly at resonance. That's the, let's say, the creme de la crop of the goal. After the half cylinder is calibrated, we want to move on to the other variants, which is the half sphere and trapezoidal prism, introduce a fighting PTO, test the emotion survivability capabilities, and in the future, hopefully incorporate wave propagation models and/or simulated control system. I conclude this presentation with this video, a video on simulations we carried out recently with DualSPHysics. I thank you for your attention, and if you have any questions, ask away. Thank you and have a nice day.